In this section, we are going to discuss capacitances. A capacitor is a device that can store electric charge and normally consists of two conducting objects, usually plates or sheets, placed near each other but not touching. So just as we have a plate A and which has a certain area of cross section, capacitors are widely used in electronic circuits and sometimes are called condensers as well. Capacitors store charge for later use, such as in camera, flash, and as energy backup in devices like computers if the power fails. So capacitors also block surges of charges in devices like computers if the power fails, or if there is an abrupt high voltage surge or something like that. Very tiny capacitors serve as memory for ones and zeros of the binary code in random access memory in RAMs of the computers and other electronic devices. So capacitors serve many other applications as well, some of which we will discuss here. So there are different shapes of capacitors that we see around. Even in your computers, there might be very small capacitors, and there are big capacitors as well, which we call condensers. So basically, your one is a parallel plate capacitor, part A that you look at. It has one end is positive and one end is negative. Your B is a we call this as a cylindrical or rolled up parallel plate. So if it's a parallel sheet which has one end positive and one end negative, and then you roll it over, that's a cylindrical shape that it acquires. And some of the real capacitors that we also see in our circuits can resemble these shapes. So they the two different ends do not meet. They are, one is positive, one is negative. So the symbol of a capacitor is basically used as this way, where one side is taken as positive. So it has a positive charged plate and a negative charged plate. A simple capacitor consists of a pair of parallel plates of area A, separated by a small distance d. So we devise our formula around this shape. Often you have them, if you roll them up to form a cylindrical paper cylinder like this, but still we have two ends where one lead is connected to the positive terminal and one is connected to the negative terminal. So parallel plate capacitor connected to a battery. So the symbol of a battery is generally this way. This is the battery symbol, where we have one end longer. The longer end is positive and the shorter end is treated as negative. And for the capacitor, both the plates are of same size. So that's the symbolic representation of what you see over here. If a voltage is applied across a capacitor, but by connecting the capacitor to a battery, just as we have done over here, charge flows, so charge Q flows from the positive end of the battery, which is the conventional current, and the other end is negative. One plate is positive, one plate is negative. One plate acquires the negative charge, while as the other plate has an equal positive charge. Each battery terminal and plate of the capacitor connected to it are at same potential, and hence the full battery voltage appears across the capacitor. So if you are sending out 12 volts, the entire 12 volts will be received by the capacitor. For a capacitor, we have a general formula. It says the charge is directly proportional to the voltage, which is potential difference. By the way, delta V from henceforth will be denoted as simply V, okay? Or in your textbook, the potential difference was VBA or VAB. So from now on, up till the electricity and when we move into proper electricity chapters, the potential difference will be denoted by symbol V. for convenience sake. We are not into going to use V, delta V for the potential difference henceforth. Beyond this point, you are used to using V for electric potential, but once we start electricity, V will be same as delta V. I just want to reiterate it. Here I'm using the V, which is potential difference. So when we remove the proportionality sign, Q is, we have to replace the proportionality sign by some constant, and that constant is capacitance, which is a constant for a certain material or a certain shape. So this constant is called capacitance. There's no mathematical derivation for this. It's the, if you're increasing the voltage, your charge is increasing. And until a certain maximum voltage is reached, beyond which the capacitor cannot charge, it gets saturated. So the unit of the charge is coulombs, we all know. The unit of the potential difference is volts. Then what is the unit of capacitance? So it seems we have named it after the scientist Farad. The unit of capacitance, if we have to find capacitance, it's Q over V. So coulomb over volts. 1 coulomb over 1 volt has been named as Farad, 1 farad. So farad is the unit of capacitance. Common capacitors have capacitances of the range of 1 farad capacitance is huge capacitance. We generally have very small numbers. 1 picofarad, picofarad. 1 picofarad is 10 to the power of minus 12 farads. You learnt about nano, 1 nanofarad, that will be 10 to the power of minus 9 farads. 1 microfarad, that will be 10 to the power of minus 6 farads. So do remember the nano, micro, milli, pico, and also the mega, giga, and all of those terms, the higher orders as well. So again, reiterating, from now on, we will simply use V as the potential difference until the electricity chapters are over. For electrostatics, we were using delta V as the potential difference. Also be sure not to confuse the coulomb with the C. C is a capacitance. Know where to differentiate between C and V, and that is why I would reiterate creating your list of formulas. So for example, it is symbol or maybe quantity. Physical quantity first, symbol, and units. For each chapter, you should create this. So physical quantity, if I say V, physical quantity potential difference. So potential difference, the symbol is V, so it's voltage, and units are volts also. That's what is confusing because volts and V resemble. Then it's charge. You already know charge is Q and the unit is coulombs. Funny thing, capacitance. Symbol is C, unit is farad. So you'll have to create this so that you don't get confused between the symbols and the units. Apart from that, we can start working on one of the formulas. It's a very simple one. We have been provided with an 8500 picofarad capacitor. So that's a pico. And you know pico is 10 to the power of minus 12. holds plus and minus charges of 16.5 cross 10 raised per minus 8 coulombs. What is the voltage across the capacitor? So you're basically using the formula Q is equal to CV to work on this. So Q is equal to CV. I already know the charge, and my job is to find V. So that will be Q over C. So go ahead and put the numbers. We have 16.5 cross 10 to the power of minus 8 coulomb as charge, and we have capacitance as 8500 picofarads, which is 10 raised per minus 12 farads. Go ahead and solve this and get the answer for the voltage. So if you are getting 19 volts, you're on the right track. So this is the voltage or the potential difference that you generally hear, as voltage is always a potential difference. Similarly, we can work on one more problem. How much charge flows from each terminal of a 12-volt battery when it is connected to a 5 microfarad capacitor? So this time, again, Q is CV. C is the capacitance, V is the voltage. We directly input our values. Capacitance is 5 microfarads. Micro is 10 raised per minus 6. And of the voltage of the battery is 12 volts. So go ahead and solve this. We end up getting 6.00 cross 10 to the power of minus 5 coulombs. So the charge on the plates of a parallel plate capacitor, if it's plus and minus, one will be 6 cross 10 to the power of minus 5 coulombs, and one will be minus 6.00 cross 10 to the power of minus 5 coulombs. Plus Q minus Q when a voltage of 12 volts is applied across the ends. 12 volts. Okay, or if you want to just draw the symbolic circuit for this, that is shorter than the actual circuit. This is your V, that is 12 volts, and that's your C, which is 6 point, that's 5 point capacitor, 5.00, 10 to the power of minus 6 farads. So from now on, you should just draw the circuit diagrams. Now we go ahead and move to the capacitance for what all is capacitance dependent on. So the capacitance C does not in general depend only on Q or V. Its value depends on the size, shape, and relative position of the two conductors. That means if I have a parallel plate, for example, if I have a parallel plate capacitor and one end is plus and one end is minus Q. So if I increase the size of the plates, so that means if I change the area, it will have a more capacity to store the charge. But if I increase the distance of separation between the plates, the capacitance will drop, not increase. Okay, so it was seen that the capacitance is directly dependent on the size of the conductor, so that is area, and C is inversely proportional to distance. When we combine the two observations, when the scientists combined the two observations, they came up with the formula C is proportional to A over D. Again, when we remove the proportionality, we insert that we have to insert a constant to make it equal. So that is epsilon naught A over D, where epsilon naught is the permittivity of free space and is 8.85 cross 10 to the power of minus 12 Coulomb square Newton meter square. So it's the same epsilon naught that we found in the value of K, which equals to 9.0 10 to the power of 9 Newton meter square over Coulomb square it's the same, E, epsilon naught. We call it epsilon. Epsilon. Okay, and so we go ahead and solve various problems and try to find out the capacitances. And so we have one problem of problem number 38 from your textbook. We have the area of the capacitor. A 0.20 farad capacitor is desired. So I want a 0.20 farad capacitor. What area must the plates have if they are separated by a 3.2 mm air gap? So using the formula C is equivalent to epsilon naught A over D. Your epsilon naught, you can rearrange this formula to get the area. What should be the ideal area of the capacitor? So go ahead and stop the video and input the values and go ahead and try to solve this. So I hope you have worked on the numbers and your area A, when first algebraically rearrange the terms, C multiplied by D over epsilon naught, and then go ahead and substitute the values. You have a 20 farad capacitance, and the distance of separation, and there's air in between the two parallel plates. So if you have a capacitance which has a distance of separation as 3.2 mm, generally these are very small gaps, a whole divided by epsilon naught, which is 8.85, 10 to the power of minus 12 coulomb square, Newton meter square, and 3.2 is your meters. So if you look at it, your answer, you can work on the numbers and get the area. So if you found out 7.2 cross 10 to the power of 7 meters square area, it's a huge area because 0.20 farad is a huge capacitance. It's a very big value for the capacitance, and hence the area to hold that kind of charge should also be huge. And you will be seeing many other homework problems like this, so work on them and you should be able to look into the problems as well. So we have one more problem from your textbook, and based on the capacitors. So if a capacitor has 4.2 microcoulomb charges on the plates and the electric field of 2.0 kilovolt per millimeter. So we also know that the electric field has a relationship between voltage as well. So if you go back to your chapter and see equation 17.8, open your textbook and you'll see that we have a relationship for potential difference in terms of electric field and volts per, where we give the volts per meter as the electric field. So if a capacitor has, the charge is given to you, so Q is CV, which is C times, C is the capacitance, epsilon naught area over D, the distance of separation for C, and volts. Instead of volts, we can write it in terms of, if you go back and see the equation for E is equal to V over D, right? So instead of writing V, we can write E multiplied by D. Okay. So writing V as E times D. And you can go ahead and solve this. So you can see that D and D is getting cancelled. Your charge is basically epsilon naught A and E. So your job is to find area. So area will be Q upon epsilon naught and E. The electric field is given to you. So go ahead and substitute the values. For charge, we put 4.2 cross 10 to the power of minus 6 coulombs, whole divided by 8.85 cross 10 to the power of minus 12. The units you can put are all in SI units. But remember, 2.0 kilo 10 to the power of 3 volts per millimeter, that is 10 raised per minus 3. So 2000 volts divided by 10 raised per minus 3. Plug in all these numbers carefully in the calculator and determine the area, which is 0.24 cubic meters. So if you see the comparison between the areas for a small charge, 4.2 microcoulombs is a small charge, and the capacitance for this can also be calculated if we had to, but the area required is 0.24 meter square, not cubic meter. Cubic meter is for volume.